I'll tell you a little bit about things I've been playing with for the last couple of years in this space of trying to understand substructure. And I just want to emphasize what we are in some sense been thinking about at least in this afternoon is our only evidence for dark matter is through its gravitational interactions, right? And it's not for want of trying. Like there have been a couple of decades of direct, indirect, and collider experiments, and they've all come up with extremely strong constraints, but no evidence for its non-gravitational interactions. And this behooves us to think very seriously about the nightmare scenario, right, where gravity is the only interaction. And one way we know to do that, I've been doing it in some sense subconsciously, and that's one way we have learned a lot about dark matter, is to look at dark matter halos, right? And it turns out that you learn a lot about dark matter microphysics from this, right? Like just to provide you examples, like from things like clusters, we learn about self-interactions. We have talked about this in the today before, right? There are galaxy scale anomalies which might or might not exist, but still seems to give hints for self-interactions. Then things like dwarf galaxies set limits on the ultralight dark matter mass, or the lightest the fermion mass can be if dark matter or a fermion, right? And what I want to ask today is, can we go smaller, right? And just to put things in perspective, again, this is probably a very obvious slide for this audience, like the things like galaxy clusters, galaxies, dwarfs, UFDs. But as soon as you start reaching the newest player in the game, the ultrafaint dwarfs, you see that there are roughly only 1,000 stars, right? And much below, these halos are gravitationally too shallow such that they do not form too many stars. And so we lose one of our, probably the only way we learn about these dark matter halos, which are these stellar tracers, which makes it extremely hard to go after these smaller structures, right? And you could ask, hey, if dark matter doesn't scatter with me, if it's only gravitationally, should I care about this dark matter at all? Like, what's the fun here, right? And this slide, in some sense, is providing you all the fun things you can think about, right? Like, so there have been talks about SIDM. I just want to provide you a whole zoo of models that could exist, right? These could be models, or even something like the primordial power spectrum. It would be very nice if we could understand what the primordial power spectrum looks like on small scales, and and how you would learn about that is, for example, from enhanced substructure in these scales, right? And then some things like ultralight dark matter, right? And generically, that predicts a k-cube tail, right, at small scales. And there is also a free streaming scale for ultralight dark matter, right? So there is a very weird interplay here where opposite things happen. So this could lead to either presence or washout a substructure on very small scales. Or things like warm dark matter, which has often been like the poster child for how to convert small-scale structure limits into interesting dark matter models, right? Or more recently, things like SIDM gravitational collapse, which we have talked about a lot. Things like early matter domination, or more recently, things I think about, which is things like long-range forces. Can you help gravity along by dark matter having a new fifth force, which is EP-violating, but nonetheless that leads to prodigious structure formation, much more than you would expect from gravity alone, right? So let me just start with that one example. The first bullet point in some sense, which is the primordial power spectrum. Right now we see it roughly a few megaparsec inverse, and this is the Planck BAO extrapolated, and these limits come from Firas, right? At much larger case, these are the existing limits on this parameter space. And then this is a playground in some sense, right? And this is not a coincidence that the pivot point is here. I've just picked the correct ultralight mass that would look like this, that would create a power spectrum that looks like this, right? And this is not ruled out today, right? Or this is not constrainable today to put a positive spin on it. Or people have thought about more exotic models, like, for example, very narrow power spectra. Why? In order to squeeze all the primordial black holes they want to produce in tiny windows which are still allowed, right? Or maybe your favorite inflation models does look something like this, right? Either way, these things are allowed, right? And I think it's very important to think about smaller scale structure, right? So you can ask next, okay, let me assume that such small and dense substructure exists. Let me call them clumps for this talk, just to differentiate it from, structure, substructure. This is really substructure, but let me just call it clumps because it's too wordy. And large power at small scale, so let me just think about the high power spectrum, but you could think of any other model, will produce small yet dense substructure. And hierarchical structure formation would mean that these small clumps, these very clumps that we are interested in, would be seeds for larger halos, right? Especially if they are much denser. This is a definite possibility. And such that, let's say you took a dwarf galaxy, just to provide a particular example of a halo. So this is the dwarf galaxy halo. These dark matter clumps could be sitting right in there. And they would be, there are some stars generically, and I'm going to use all of these in the next couple of slides. Right? And this has been noticed before, and it's just some very simple thermodynamics. Okay? So in the limit where the mass of these clumps, which is sitting inside these dwarf galaxies, in the limit that these clumps are more massive than the individual stars, you see that the kinetic energy of these clumps, which is given by some m clumps, say, multiplied by the dispersion, m clump sigma square, you will notice is much larger than the kinetic energy per degree of freedom of the stars, right? So to use the concept of thermodynamics, there is a hot fluid and a cold fluid just sitting co-located in this gravitational potential. Right? And the hot fluid being the clumps, and the cold fluid being the stars. Right? And we know what happens if you set up a hot fluid and cold fluid right next to each other. Thermodynamics will imply that there is heat transfer from the clumps to the stars. Right? And what is the interaction? We could ask, okay, the one interaction I know is just gravity. What does that do for me? Right? Is there sufficient interactions between the clump and the star such that the star system gets heated up? Right? And it turns out it does. You can just calculate it. So here I'm just keeping it general. There is some gas A, and then the total amount of gravitational heating, so that's why you see g squared here, is proportional to the density of the B fluid times the mass of the individual component of the B fluid times the velocity dispersion. Right? And then again, of course, there is one more power of m here. Why? Because for gravity, if you want to think of it like Coulomb-like scattering, the mass is the charge. So the more the mass, the more the interaction strength between the two fluids. Let me now go to the specific case of stars and clumps, right? So how much heating is happening in the stars? You see, again, as I told you before, it's proportional to the density of the clumps in your ultrafaint dwarf. It's proportional to the mass of the clump. The more mass of the clump, the more heating that's going to happen. And it's inversely proportional to the velocity dispersion of the clump. So it's clear what kind of systems you should be interested in to possibly see this heating effect. Right? It should be systems with the largest dark matter densities. After all, that's where you would find the most clumps as well. And systems with extremely small velocity dispersions. Right? And it turns out both are found in ultrafaint dwarf galaxies. In fact, that's where this ratio is maximum. Right? So that's a natural place to study this, and just some numerics to help move things along. So you could ask, okay, how much does the star system expand because of this heating, right? And first things first, these are extremely old stars. This is well known from their metallicities. They are roughly 12 billion years old. So these bolometers, in some sense, these astrophysical bolometers have existed forever, right? And and it turns out they're very sensitive bolometers. Why? Because if you put 100% of dark matter in clumps, again, this is just a thought experiment, okay? 100% of dark matter in these clumps, and the mass of the clump is, say, 100 solar masses. I want it to be larger than a solar mass, so let me put 100 solar mass. And putting in like the velocity dispersions that we observe, what you find is that the star system should expand to around 100 parsec or bigger. Right? What this slide is telling you is, again, I'll come back to this in a moment. You don't really depend on the initial half-light radius of these stars. You will build for yourself a star system which has an extremely large half-light radius. Okay? There's a caveat here I can explain to you later if you're interested in this. But the point is that we do observe many ultrafaint dwarfs with much smaller half-light radii. Okay? So right around the 25 to 30 parsec range. And this seems in conflict with the existence of extremely dense clumps in your system, right? And this should set stringent constraints, right? And so let's unpack this. So first, let's simplify our lives, and let's make these clumps really PBHs or machos. Okay? Let's simplify our lives because I don't need to worry about things like tidal stripping. I just want to show you what things look like, and it turns out there are lots of interesting things to say about PBHs themselves, right? And all this was done before, right? Whatever I've told you till now was identified in 2016 by Brandt, who set these constraints from compact UFDs precisely from this effect, right? So you see the 1/m behavior that I was just telling you about. So the fraction in dark matter that's plotted in the y-axis versus the macho mass. So you can think of these as primordial black holes if you want. These are just point objects for this study. And what Brandt sees is that you can take the initial half-life radius to be 30 or 2. There are small modifications. There's only small changes in the limits that you set from the non-observation of a larger half-life radius. Okay? So you could ask, okay, what's new here? And we were very surprised that one particular very interesting effect was missed in these previous papers. It was known in other contexts, but not in the context of ultrafaint dwarfs, which is that in the limit that the fraction in machos or PBHs is much smaller than 1, we should not think of them as 2 fluids, which I've been talking about, but really 3 fluids, right? What are they? They are the machos, they are the stars, which I'm not showing you yet, and the smooth dark matter, right? So you should put that itself also in. And then now the smooth dark matter, which you could take as 0 mass if you want, has a much smaller temperature than the machos, right? What this means is that there is, another way to say it is there is dynamical friction on these machos, right? So it's the exact same thing. You should expect the machos to migrate inwards. And this is especially dire in something like an ultrafaint dwarf galaxy where the velocity dispersion is extremely small, right? How dire is it? I will show you in a second. But notice that this is especially bad for these stars sitting at the center, right? Because that's exactly where these machos are ending up. So you should expect much larger heating than you would have naively expected if you didn't take this effect into account. Right? So there is even more heating than you would expect that was not there in Brandt's paper. And so we put this in. So this was Peter Graham and I in 2013. And we find that if you exclude migration versus include migration, this is ultimately the plot for machos or primordial black holes coming from ultrafaint dwarf heating. Once again, the y-axis is a fraction in machos, and the x-axis is the mass of the machos. And what's very important is that you can set constraint down to 10 solar masses or so, right? So in the case that is literally the definition of F macho. How much of the ultrafaint dwarf galaxies? No, this is local definition. Right, it's a local definition. I mean, when you see F macho limits from, say, Eros or Ogly, they're doing exactly this. They're right. Okay, yeah, good. Excellent. So this is where I would stop if I were only talking about primordial black holes. Of course, this is the right-hand side, too few clumps in these ultrafaint dwarfs or too few machos. Now you can ask, okay, let's put things back. Let's complicate our lives a little bit more by considering clumps, right? More or less diffuse objects. And this is what I ultimately wanted to do before I realized that this migration was missing before. So let me model these clumps as just NFW cores, right? This is a little bit of a cheat, but why I'm doing this is A, to make my life simpler, but B, because I expect the wings of the NFW to be tidally stripped anyway. Okay? So this is not a great approximation, and these are things you can criticize, and these are things I hope will get addressed in due course. But let me just show you some interesting physics, okay? First, you can ask, okay, let me forget about all these clump destruction effects, right? Let's just understand, as I make these point objects more diffuse, what happens to the heating rate? I can just ask a heating rate question. So that's the plot I'm showing here. where I'm plotting here rho, the density, as a function of mass, and what fraction of the UFD could be in these clumps. Right? So the PBH plots or the Marshall plot I was showing you are at infinite density if you want. Right? And what you're noticing here is that there is almost no effect. There is very, very limited effect by reducing the density of these machos. Right? Why is this happening? It's happening because of something we all know very well, which is that in long range, this is really Coulomb scattering. Right? And for Coulomb scattering, decades in impact parameter contribute equally to the cross section when you're thinking about, say, something like a momentum transfer cross section. Another way of saying this is that there is a Coulomb log sitting here. And the Coulomb log is the only way you can, only place where the minimum impact parameter enters. In other words, you could make the impact parameter 100 times, 1,000 times, and you'll only contribute as a log. You'll only lose as a log in the heating rate. Right? And that's why something like this is happening. And the point of this plot, in some sense, is that all of the fun now is in understanding whether the clumps do survive the UFD or not. Even little lower densities, as long as they are present, will heat your star sufficiently, as long as they are massive enough. Right? So unfortunately, I won't have time to go into the specific processes, but the ones I consider are things like clump harassment in the UFD, tidal disruptions from the host UFD, things like tidal disruptions in the stars. Again, I'm happy to go over it later, but I'll tell you just what we find. What we find is that now you see there is a more severe effect as you reduce the density. For, say, 10 to the 6 solar mass per parsec cube, again, remember, these are just purely NFW cores. There is nothing, no wings, none of it. Again, this is just a place to start. And also, all of these cores are monochromatic. Yeah, there is no extended halo mass function. These are delta function halo mass functions, if you want. Again, this is just a toy model to just explain what happens when you have more diffuse objects. But what's interesting, and I think it's very powerful, is that you can go to low densities. You can go even to 100 solar mass per parsec cube or 10 solar mass per parsec cube. And this is barely 10 times more dense than the ambient UFD density at its core. Right? And you notice that that also sets limits. That's also ruled out by the non-observation of a large stellar half-light radius in your UFD. Right? Now let me show the same plot in a different axis. So here I'm plotting rho now, and here's M clump, or in other words, the primordial black hole would have been up there, and then as you reduce the density, what's happening? And I'm plotting what fraction of clumps are ruled out locally in the UFD, right? And what is very interesting is you can rule out fractions as small as 10 to the minus 4, right? 100% might not be too interesting. Why would 100% of dark matter be in exactly the same monochromatic cores? But I hope you can appreciate that fractions as small as this start becoming super interesting. And these fractions happen to be so small precisely because effects like migration happen in a ultra-faint dwarf because of the large density. So if these large clumps exist, 10 to the 4, 10 to the 5 mass, solar mass large clumps exist, they actually start spiraling inwards, helping out the heating that is happening in the center. Yes?
You keep hammering on the over-diffuse cores.
Yes.
This is scale-free, right? This should happen in any halo mass because the velocity dispersion drops out.
No, it doesn't. The heating rate is inversely proportional to the velocity. To the velocity dispersion.
The heating rate, but so this is at a particular mass scale for velocity dispersion of a given system.
Yes, so I'm assuming a 10 to the 9 solar mass UFD. If you did the same game in a dwarf galaxy, which is much larger, like say 10 to the 11 solar mass, you will not see these constraints. And furthermore, the half-light radius of a dwarf is so big that it's a much inferior bolometer, if you want. It's much less sensitive to the same amount of heating rate. Good. So that, in some sense, is the limits. So let's go back to this first model I was talking about, the first application I was talking about, which is just the primordial power spectrum, right? Again, I'm not doing the most sophisticated analysis here. These are just, plots to provoke you, if you want, right? Is to ask, let's say I injected some power in a very, very small, small spread in K, right? Say half an order of magnitude in K, right? And I want to ask, okay, if for such an isolated high power, what does finally substructure look like? So I just did some pressure sector analysis of something like this, and then assumed that the UFD samples the dark matter density when it collapses. And what we find is that we can set constraints on such a power. Again, remember that this is almost a delta function if you want. Right? It's an extremely isolated power, isolated amount of power, and this is the average power in that particular K. And you see that we set constraints all the way down to a kiloparsec inverse from the non-observation of stellar half-light radii. And this, in some sense, is the power of this, which makes me very excited, right? And then this is more speculative stuff. Okay, so. More recently, this was Julio Navarro et al. Who talked about these Ursa Major 3, right? Very recent observation. I know this is pretty controversial because the velocity dispersions are still not very well known, except they find an object which has a total stellar mass of roughly 16 solar masses, and these are just the stars, and a half-light radius of all 3 parsec. It's tiny, right? And which makes you wonder, hey, is this an even better bolometer, right? Again, this is just speculation, but you could ask if in the future this was confirmed, or if a UFD was found with parameters like this, what would that tell you about dark matter, right? So this is just a preliminary plot to show you how powerful it is. You see that this was our previous limit in green, 2311, and this is where your constraints would improve because Ursa 3 is predicted to be so dense, and because its half-light radius is just so tiny that even an even smaller amount of heat transfer would have a very drastic effect, right? So we are now going to close to the 1 solar mass range. Again, this is very speculative. I'll be the first one to admit, but this is just to show that if such observations are made, what you can do with something like that, right? And then this has led to follow-up work, which I wanted to show you. Again, it has a lot of applications to particle physics. What these authors show is that if there's a post-inflationary axion, generically it leads to axion mini-clusters and subsequently axion stars. And these axion stars essentially act as machos. They're very dense. And as a result, you can set limits on, with minimal assumptions, you can set limits on this post-inflationary scenario. This is for axion-like particles, not QCD axions. So they're not getting any mass from the QCD scale up to around 3×10⁻17 eV. They're using our work directly to set strong limits like this. So that's about what I wanted to tell you about substructure. In the last couple of minutes, I will tell you about some other things you can do with UFDs or other galactic dynamics things, like if you have some kind of information about it, which is you could ask this question: hey, if there is 2 baths, A and B, this is the heat transfer, right? You could immediately ask, I constrained interactions between extremely large clumps and stars. You could ask, could I constrain just dark matter itself, right? Could I constrain dark matter itself? Again, that is equivalent to setting MB's mass to 0, right? It's equivalent to constraining setting MB's mass to 0, but you see there is still this term rho B times MA. Yes? And you see the negative sign. What it's telling you is that the stars are now sitting in a very cold fluid. Yes? Unlike before where they were sitting in a hot fluid, the stars are now sitting in a cold fluid, and the stars would just contract. Right? And you might already guess where these numbers are going. Remember, I could only constrain 10 solar masses or below, right? Whereas the stars, by definition, are around a solar mass, yeah? And because the stars are a solar mass, if you waited 100 gigayear, you will actually start seeing this effect, where the stars would just start contracting because of the effect of UFD. If you waited long enough, there is dynamical friction. That's the point of this slide. But a corollary of that is if there was a new force between dark matter and standard model that resulted in effectively increasing G, right? That you could already start constraining. Irrespective of what dark matter mass was, as long as this g was bigger than g Newton for a dark matter standard model force at relatively smaller ranges than what is already constrained, that you could constrain now. So we worked that out, and this is a very complicated plot. I don't want to unpack it, but I would encourage you to read this. So this was led by Zach, who was a grad student at Stanford. He's at Fermilab now, and we set some very nice constraints on much shorter ranges than what cosmology, in some sense, structure formation can constrain in this particular parameter space. So this is alpha SD. How much stronger than gravity is your force, right? And we're talking about much smaller ranges. So that's why much stronger than gravity is allowed. But don't get put off by this how large alpha SD is. So I just want to emphasize this is not the fine structure constant. This parameter, in some sense, is how much stronger than gravity your force is. So this is an extremely weak force from just looking at alpha SD numbers. Okay. I also want to very short advertisement to something else we did. We looked at the bullet cluster and noticed that no one had made this particular plot, which is again alpha DD, dark matter cross section. How does that look like? Dark matter self-interaction force. What does that look like as a function of lambda? For lambda much smaller than say the size of the bullet cluster itself, where there's just residual coherent interactions between the two bullets, right? Again, this is very simple stuff. It's not that complicated. No one just done this before, so this is just a plot of what that looks like when such a force exists between the two, right? So I will give you the outlook and conclude. What I just showed you was that things like the primordial power spectrum, say models of inflation, or things like SIDM, gravithermal collapse, or even things like axion self-interactions or long-range forces that cause early collapse, or atomic dark matter. I know people in this room work on all of these models, right? And they all typically predict prodigious substructure, prodigious small-scale structure, right? And this seems to be a very powerful probe of these family of models which produce large substructure. Perhaps even other models like I didn't talk about today, like things like primordial magnetic fields that could do this. Like there's lots of opportunity here to constrain these things. I'll just conclude. So probing small-scale structure below the UFD scale is very difficult. UFD dynamics, ultra-faint dwarf dynamics, seems to be constraining this dense structure down to 10 solar mass today, maybe lower 1 solar mass. If things like URSA are confirmed, there are applications to things like SIDM that I'm working on, or other structure-forming dark matter, non-trivial dark matter dynamics. And galaxy dynamics can also probe long-range forces. I just showed you that in the last couple of slides. Thank you.
So we had a couple of questions during the talk, but does anyone have one or two quick questions? Yeah, Marius.
Yeah, thanks for the nice talk. Yeah, this is very interesting. One question: what would constitute detection here?
Great. So I mean, again, this is always difficult, right? Like I have some vague ideas of this. I can tell you, like for example, if there was a correlation between the half-life radius and the inherent dark matter density or something like that. So that would mean that possibly this is happening. But that is, I would be the first to admit that it's very far-fetched. Like you would need a lot of UFDs to start playing games like this. You would need to know the initial conditions because that will start contributing to what the final half-life radius is today. So it's a very messy enterprise to claim any kind of discovery here.
I think I'm a bit confused. So as far as I understand, the picture is that you have this sort of ratio, like heat transfer between two fluids. But what about violent things that happen during the history of these things?
Right.
These are not captured, I guess, by this picture. And could they be a systematic to this picture of like two fluids exchanging heat?
So violent things like what?
I don't know, mergers or baryonic
So-
explosion inside these things.
So remember, these things have to perversely cool the star system in order to erase what the dark matter is doing to the stars, right? So in some sense, if you do not come up with something, violent things in general won't do that, right? So that's the first thing I'll tell you. And the second thing I'll tell you is that people have done n-body simulations on this particular parameter space where they're just looking at the stars and modeling the dark matter as purely a friction term. Such n-body simulations exist. Again, I do not know if they're accounting for mergers as well, which completely agree with just this naive thermodynamical picture for what the stars do. And in general, I feel like if you just want to think about things like feedback and things like that, the UFD is a much quieter environment than say, dwarfs or Milky Way-sized galaxies. So that helps out a little bit also. But the specific point of question of a merger, I guess I'm not imaginative enough to think about a perverse thing that would keep the stars cooled while this heating effect continues to exist. It just sounds really contrived, but it might very well exist. I don't know.
Violent relaxation will undo all the effects you mentioned.
Sorry?
Violent relaxation mixes.
Okay.
And so it will undo both the sinking of the blobs and the relative different heats of the system. So it will. So violent relaxation exactly opposes it.
Okay.
But I mean, I agree. It's unlikely that these.
Right.